Hi, so we've discussed now about population growth rates, and we already in the past talked about what happens if we increase the savings rate. This would cause an increase in the steady state level of capital stock per capita, and this would also increase the output per capita. But one thing that we haven't really talked about is consumption. So, what about C? That is the question. So, for example, just as a quick introduction to the topic of consumption, imagine we had a savings rate of 0 in the economy. That means that all income is consumed, so consumption, which is 1 minus savings, would then equal 1. So everything is consumed in period 1, there's no saving, and then there's no income in any of the subsequent periods. So in future, consumption will equal 0. Now, what about if savings equal 1? The other end of the spectrum, everything is saved. This simply means consumption, again, is 1 minus savings, and consumption will equal 0. Everything's saved, so nothing is left to consume. So if savings are 0, consumption 0. If savings is 1, consumption is 0. So what we're interested in is if savings is anything in between all the other values of savings, and at those times we will have positive consumption. There will be positive consumption if savings is between 0 and 1. So different levels of savings give different steady states, but which is the best steady state? Which is the best level of S that we want to choose such that we can have the best steady state? And what do we mean by a best steady state anyway? So when we think about the best steady state, what we are thinking about is consumption. So in any economy, consumption gives us our economic well-being, or it gives us utility. Ideally, we want to be consuming as much as possible, assuming we don't have any satiation, and there's no limit. We're going to assume that more consumption is better. The more we consume, the happier we are. So, ideally, our best steady state will be the one that has the most possible consumption. That is our best steady state. So, how do we maximize consumption? Well, consumption in steady state we'll call C star. We know that this is equal to 1 minus the savings rate multiplied by output, and our output function is this function of capital per capita at the steady state, so it's got the star on it. So how do we maximize consumption? Well, let's imagine we increase the savings rate in this function here. Then this will increase our capital per capita, and it'll also increase our output per capita, and that can increase our consumption. So increasing saving can increase consumption, so maybe we want to increase the savings rate. But we have this other effect where increasing the savings rate will actually decrease consumption, because consumption equals 1 minus savings. So that's just a direct effect of, if we increase savings, that means we're saving instead of consuming. It's just we can only do one or the other. So we have a trade-off. By increasing savings, we can increase future consumption by increasing output per capita. So more output means there's more available to be consumed, but increasing savings means that we're saving instead of consuming. So we need to come up with a way to find the maximum point. Where is the most consumption? Which steady state gives this? So this trade-off will look something like this diagram. So as we increase the savings rate this way, from 0, as I said before, zero savings rate means there's no future consumption because there's no investment. So there's 0 consumption. And if once we save everything, there's nothing left for consumption. So a saving rate of 1, we have 0 consumption again. In between, this increases, and we have the trade-off I've just discussed. And what we want to find is this maximum point. Where can we maximize C star? So C star max. So this point is given at what we call the golden rule level of capital. The golden rule. And we'll call that K star gold. So this is the steady state value of K that maximizes consumption. And we acquire this by varying our savings rate. So changing savings changes the amount of investment we have, which will change our steady state level of capital per capita. And we're looking for the golden rule level of capital per capita, which maximizes consumption at this point here. So let's find it. So to start finding it, we want to first express C star, our consumption at steady state, in terms of K star, our steady state level of capital per capita. So we have our national income identity, y equals C plus I. So we're going to rearrange that and put it at the steady state levels. So we get a function in terms of consumption. So we get consumption in terms of this. We know that the steady state level of output per capita is this function of the capital per capita steady state level. And we also know that in this model, investment, so this investment term, is equal to the change in the capital stock plus our break-even investment level. So this comes about from our fundamental equation of capital that we use all the time, SFK plus, we have this break-even term because we now have population growth in the model. And so this term is investment, so just rearranging, we get that investment equals this. So if we plug that in, we get that C star equals FK star minus this break-even level of capital, plus, of course, minus, it doesn't really matter though, minus this change in capital. But it doesn't matter because this change in capital is equal to 0 because we're at steady state. So the capital is not changing. We're at steady state because we're evaluating at these stars. So we can get rid of this term. So we have that consumption in steady state equals our output minus break-even investment. Intuitively makes sense, so we are consuming our output except for the stuff that we're investing in order to break even. So that's the mathematical, that's mathematically showing how we derive the consumption level at steady state. So we can draw the two elements of this function on the graph. This is a graph of output and depreciation at steady state levels. So not the same as what we usually do, but we have actually got the steady state level of capital on this x-axis. So again, we've got the break-even investment at steady state and the output at steady state. So we are looking to maximize consumption. So where on this graph, which level of K star is consumption maximized? Well, as we know, consumption is this output minus the break-even investment. So the point where consumption is maximized is where we have the largest gap between these two curves. And more precisely, it's where this output FK star curve is furthest above the depreciation curve, or the break-even investment curve. Because if break-even investment is above our output curve, then we don't have high levels of consumption there because we're using our resources. All our resources are being depreciated. So what we're actually looking for is the point where this distance is maximized between the two curves, which is about here. So if we say that this is our K star gold level, so the gap between our break-even investment curve and our output curve is the greatest, and the gap between them, that is our consumption at the golden rule steady state. So that's why we want a large gap between them, because the size of the gap is how much we consume. If we're over here, we have a small level of consumption, and as we move towards this golden rule, the gap gets bigger and bigger, and at the biggest gap, that's where we have the highest level of consumption. This is the best steady state, because all of these are steady states. We're talking about capital per capita at steady state. All of these combinations of K are all steady states. This is just the best one. This one has the highest consumption per capita. And as we said, that's utility, so you want to maximize that. So how do we find this level of capital per capita that maximizes consumption? Well, luckily for us, there's a nice result we can use that says that the gap between these two curves is largest when the slope of the production function, fk star, equals the slope of the break-even investment curve. This intuitively, if you think about it, is because we're looking for the largest gap between these two curves. So if we shift up this break-even investment curve and keep shifting it upwards, we eventually get to a point where this curve is tangent to the output curve fk star, and so this tangency point will naturally occur when the two curves are furthest apart because of just how we've done this. Until we get to the point where they're tangent, we can still push this curve further up and to the left. So this is why the gap between the two curves is largest when the slope of the two curves is equal. And what is the slope of this break-even investment curve? Well, quite simple. The slope is the sigma plus n. So this is just a straight line, this curve through the origin, and the slope is just given to this. So we need the slope of the production function to equal sigma plus n. And what is the slope of the production function? This is actually the marginal product of capital. We need the marginal product of capital to be equal to sigma plus n. Why is this the marginal product of capital? Well, we have a production function in terms of k star, this x-axis I should have written is k, or it is just k actually, not k star, but no, it is k star. So this x-axis is k star, our function is in terms of k star, so we take the derivative again with respect to k star, and as a result we are getting the marginal returns to a unit of k, and so we get the marginal product of capital as when we take the derivative of this function. And as we know, the derivative is the slope of a curve, so what we need is marginal product of capital equal to the slope of the break-even investment curve, which is sigma plus n. So using this result, we know we can identify this exact point where we have the golden rule level of capital, which is very nice. So we can figure out exactly what this point is. So I'm going to do that mathematically. I've shown it graphically to give a bit of intuition, despite how shoddily I've managed to explain it, but let's derive it mathematically and hopefully it should all become a bit clearer. So as previously said, we have that our consumption is equal to our output function minus our break-even investment. So we want to maximize consumption. So we maximize with respect to k star. So both of these functions are in terms of k star, everything else is just constants that we have in there. So we want to maximize consumption with respect to k star. And so what is our maximization problem? With max with respect to k star. And the function we're maximizing is f of k star minus our break-even investment. So we do this derivative, we just do the derivative of everything here with respect to k star, so this function, and we set that equal to 0, so that's our first order condition, and that will give us the maximum. You can check the second order conditions to show that that's negative and that this characterizes a maximum, but I won't do that here. So what does the derivative of this give us? This gives us just the derivative. This depends on our production function. I'm sure we've all done derivatives of production functions with respect to k. That gives us this term, and as I said before, this is equal to the marginal product of capital. If you take the derivative of your production function with respect to capital, you get out the marginal returns to a unit of capital. And this is also equal to the break-even, the parameters that are on the break-even investment, because we're differentiating this term here with respect to k star. So what we get out of that is just this negative sigma plus n. And so we basically, just to fill in some steps, the derivative is this, the derivative of that is this, and we set that equal to 0, and of course then we get out this result here, that what we need to solve for the golden state, or the golden rule steady state, is that the marginal product of capital equals this, equals sigma plus n. So this marginal product of capital will be in terms of your k star, because that's the only variable in the function, and then we can simply just rearrange this for k star in terms of parameters, and then from that you simply have your golden rule level of capital, and again from this you can derive what your savings rate should be to allow us to reach this golden rule steady state. So in the past, when we looked at just steady states, we saw that the economies tended to converge to their steady state. However, when we're looking at the golden rule steady state, we must note that the economy does not naturally just move towards this golden rule steady state, because we've basically chosen a steady state such that we have maximum consumption. There's no reason that an economy left to its own devices will converge to this golden rule. It could converge to a steady state that has maximum consumption, but that is highly unlikely. It's much more likely that we converge to some other steady state. So how do we get to the golden rule? We have to adjust the savings rate, as I've mentioned, and if we choose this savings rate that maximizes, as I showed before, this function, if we choose this savings rate, then the economy will converge to the golden rule steady state. There are a number of policies that a government may decide to implement to affect how much people save, and so that is the way that policymakers would look to reach this best steady state. So I'll do another quick video just talking about transitioning to steady state, as this one's getting a bit longer, but that is the basics of golden rule steady state and how we develop it. Make sure to check out the next video where I discuss the transitions, how a policymaker can make sure that we transition to the golden rule by checking out the playlist. Subscribe to get future videos, and if this was at all useful, please do leave a like. Thank you.